Okay, so let's start talking about algorithms finally. And I should say that I don't want to be the talking slides. So in this case, here the slides are very verbose. You can read them. I just am going to go to what I think are the main points. So maybe let's first think about algorithms. So algorithms are, the recipes of solving specific problems, right? And they are made of atomic or primitive instructions that are very, very simple, and each one can be handled in constant time. Algorithms have finite descriptions. We don't want infinite algorithms. And of course, they have memory and state and so on. A computer, on the other hand, is the hardware upon which we run the algorithm, right, the program. And, it has essentially assembly language which execute those basic commands of the algorithm. Okay, now it's really important to understand what model of computation we are using. So we are going to use what is intuitively equivalent to a regular computer with an assembly language, right? So every atomic operation would take constant time and more or less the same time, and that's it. Now, of course, we are not going to work in the Turing machine model because it's too low level and too painful. So we're going to use this unit cost RAM model. Now, generally speaking, it's a very good model to capture how real-world computer behaves. Here and there would be cases where it would be like, no, this is not true. This is not really how real computer behaves. So our model is really giving us the wrong answer. But most of the time, it would be more than good enough. Okay, so what is the RAM model? We have essentially RAM means that we have read random access memory. So we have, you can think about it that we have an array, or if you want even an infinite array, because we are not going to care about the size of memory. And you can in constant time read from memory, write to memory, and we are going to assume the regular, ability to do basic operation like read, write, and so on. We're not going to worry too much about how much information is going to be stored in the cell of the memory. So the cell of the memory would store a word, and word for our purposes are, sufficiently large to hold whatever they need to hold. So we don't have to worry about a numerical overflow and stuff like that, whether we're using 32-bit or 64-bit or 128-bit. This is all low-level stuff that we are not going to care about. Okay. Now, why do we have to be careful about the RAM model? So the problem is that since we don't care about the size of the words can be arbitrarily large. The problem is that if you're not careful, you can do a lot of very magical things, right? So you can, in particular, for some problems somehow, store all the input in one word of memory, and now you can start doing operations on those words. And in particular, it turns out that if you allow me a RAM model and some bizarre operation like floor and ceiling, and I think you might need division or log, doesn't really matter. If you give me those, the first bit as its own operation. So if you allow me a RAM model with a few kind of slightly less standard operations, which are completely standard in a regular assembly computer, then suddenly you can run program that takes exponential time in linear time, right? So that's really bad, because essentially what happens is that the words can, the amount of information you can store in a word can become exponential. The details are too technical. We're not going to cover this in the course, but intuitively, if the words that we are using in our algorithm becomes unbounded in size, we will stop and say, this is not really how a real computer works, and as such, our model here fails, right? So in particular, you can think about basic things like multiplying two numbers, where you really want to multiply huge numbers, right? Now, why would you like to multiply huge numbers? Well, our basic crypto system that we are using on everything, RSA, essentially relies on thousands of digits, prime numbers, that you multiply them and so on and so forth. And you need to be able to multiply, such large numbers. And they definitely don't fit into the worlds of regular computers, right? So now you have to essentially implement algorithms that really can multiply huge numbers. And, it doesn't take constant time to multiply them, right? The time to multiply them is a function of the number of digits, right? So when we get to this fork in the road where, we need to be careful about the size of the words, we will explicitly say so. But most of the time, we don't have to worry about it. And you can just assume that, words are unbounded and we don't have to worry about this low-level nonsense. So we are assuming a unit cost model, RAM unit cost model, and whenever it breaks for our purposes, we will say so explicitly. This is it for now.